Hello everyone, this is Sinja Sharma, engineering physics third year student, and today I'm going to present and demonstrate the Hall effect experiment. Outline of the presentation. First of all, I'll introduce you to the Hall effect and then we'll discuss the apparatus of Hall effect. Then we'll be performing two experiments. First to demonstrate the Hall effect, measure the Hall voltage and charge carrier concentration. And then to study the relation between the Hall probe width and the Hall voltage. Then we'll be discussing the results in the conclusion and then the applications of Hall effect. So what exactly is Hall effect? As you can see in this figure, when a magnetic field is applied to a conductor carrying an electric current, this causes the charge carriers, which are usually electrons in the conductor, to experience a force which is perpendicular to the direction of their motion. Now this force causes the charge carrier to deflect from this straight path and start moving in a circular motion, as you can see over here. So as a result of this deflection, these charge carriers accumulate to one side of the conductor, which creates an imbalance of charges. So this accumulation of charges also creates an electric field which is perpendicular to both the magnetic field and the direction of electric current flow. So this electric field further produces a voltage which we know as the Hall voltage. We'll study and measure the Hall voltage in our experiment today. So apparatus for the experiment. So I'll start by explaining the apparatus of the Hall effect setup. The first is the germanium N-type and germanium P-type Hall probes, which we will insert in electromagnetic connected to the digital Hall effect setup to study the variation of voltage with current at a constant current power supply. And also we have digital Gauss meter we will be using in a first step with this Hall probe to explain to study the variation of current with the magnetic field. So, what experiments are we performing here? Like I already told you, we'll be performing two experiments today. So, we'll start with the first experiment now. To demonstrate the Hall effect and to measure the Hall voltage and the charge carrier concentration in a sample material, which in our case are germanium N-type and germanium P-type. The Hall effect experiment consists of various steps. The first step is to study the variation of constant current power supply with the magnetic field, for which we will be using the Gauss probe and digital Gauss meter. And the next we will insert Hall probes, germanium P-type and germanium N-type in the electromagnet instead of this Gauss probe, and use the Hall effect setup and to study the variation of current and voltage at a constant current supply. So in the first part of the experiment, I will study the variation of magnetic field with changing current, and for that I have already inserted the Gauss probe inside the electromagnetic current to the digital Gauss meter. So I will turn the constant current power supply on and digital Gauss meter on. So as we can see, as the current increases, the magnetic field also increases. So now I'll increase the constant current power supply using this knob in steps of 0.5 ampere to study and record the corresponding magnetic field in the extend range. So the first reading at 0.5 ampere, at 0.52 ampere we have 490 Gauss of magnetic field. The next reading at 1.03 ampere is 950 Gauss. Similarly, as we increase it to 1.54, we have 1400 Gauss, and further I'll record it up to 2.5 ampere. So these are the observations I recorded from the experiment, which turned out to be linearly related. So the current and the magnetic field are linearly related. As we increase the current, the magnetic field also increases. So in the second part of the experiments, we will use two Hall probes, germanium N-type and germanium P-type, to study the variation of the Hall current with Hall voltage at a constant current power supply. So I have kept the constant current at 1 ampere, and I'll change the Hall current from the digital Hall effect setup and will record the corresponding Hall voltage. So I'll do this in steps of 2 milliamperes. So the first step, at around 2 milliampere we have 2.8 millivolt of current voltage. So in the consecutive input of around 4 milliampere, we have 6.8 millivolt of voltage. At 6 milliampere of hall current, we have 11.5 millivolt of hall voltage, and similarly I'll increase it up to 12 milliampere to get 6 readings and will record it. So I've kept the So these are the observations I obtained from germanium p-type and germanium n-type hall probes at keeping the constant current power supply of 1 ampere. As we have already seen in the previous part of the experiment, that at 1 ampere the magnetic field induced B is equals to 970 Gauss. The thickness of the germanium crystal we use is 0.05 centimeter. So I have plotted these observations separately for the p-type germanium and the n-type germanium probe. So, as you can see, the current versus voltage relationship for both germanium p-type and germanium n-type comes out to be linear. However, as the slope is positive in germanium p-type, the slope comes out to be negative for the germanium n-type. So, calculations and results. We have calculated the Hall coefficient RH in the current density, Ne, in both the cases. So for germanium p-type, the Hall effect RH turned out to be 9.74 into 10 raised to the power 3 centimeter cube per coulomb, and the current density is turned out to be 6.41 into 10 raised to the power 14 per centimeter cube. And the for germanium n-type, the Hall coefficient RH is minus 1.11 into 10 raised to the power 4 centimeter cube per coulomb, whereas the current density is calculated to be 5.778 into 10 raised to the power 14 per centimeter cube. Now we'll move on to the experiment number 2, where we'll study the relation between the Hall probe width and the Hall voltage. For the second experiment, I have chosen this virtual lab by Amrita University. In this, I've already selected the Hall effect setup, and I've already set the constant current supply to, let's say, 2 ampere. So our selected material is germanium, and as we increase its thickness, we see the variation in the Hall voltage. So at 0.2 mm, we have 28.756 millivolt of Hall voltage. At 0.3 mm, we have 19.171 millivolt of voltage. At 0.4 mm, we have 14.378 millivolt of voltage. And further up to 0.9 mm, we'll record the readings. So the observations I noted down in the experiment are these. As we increase the width of the Hall probe, that is germanium crystal, in steps of 0.1 millimeter, this turned out to be like this. The graph turned out to be hyperbolic, that is, as the width increases, the Hall voltage decreases. So, the conclusion or the result of the two experiments, we found out that I versus V plot is linear for both germanium p-type and germanium n-type. However, while the slope is positive for the p-type germanium, it is negative for the n-type. And as we increase the width of the Hall probe, the Hall voltage decreases. Now, the applications of Hall effect. First, magnetic field sensing. Hall effect is commonly used in magnetic field sensors to measure the strength and direction of magnetic field, which are widely used in various applications such as compasses, magnetic levitation systems, non-contact position sensors. Second, current sensing. Since we know the Hall effect can also be used to measure the magnitude and direction of electric current in the conductor, thus it is often used in electronic devices such as power meters, battery monitoring systems, and motor control systems. Third, proximity sensing. Hall effect is used in proximity sensors which are used to detect the presence or absence of a nearby object. Now these Hall effect sensors are commonly used in industrial applications such as automated machinery, robotics, safety systems, etc. Fourth, quadrilateral position sensing. The Hall effect can be used to detect the position of a moving object without physical contact. So these sensors are used in automotive applications such as throttle position sensors, speed sensors, gear position sensors, etc. Material analysis. The Hall effect is used in material analysis to determine the properties of materials such as the resistivity, carrier concentration, and mobility. This information is used to design electronic devices like transistors, diodes, integrated circuits, etc. Some other applications of Hall effect include magnetometry, semiconductor characterization, etc. That's all. Thank you.